Hi everybody. Today we are going to be talking about files. In the Unix world, the files stored in the file structure are a little different than you might be used to, especially if you're coming from a Windows background. So today we are going to look at the way files are represented to the operating system, how we interact with them, and how we can get information about them. So to start off, files on Unix are going to be inodes with hard links that point to them. So that's a couple of new terms for you. So an inode is maintained by the file system, and it contains pointers to where the actual file data is located on the drive. The inode also contains the meta information about that file. That's the size, that's the permissions, that's whether or not the sticky bit is set. Those are part of the permission structures. Lots of different interesting things. It also has a reference count stored in the inode, which is how many hard links are pointing to that inode. And again, we haven't defined hard link yet, but and then finally the inode has a unique inode number, i.e. they're all unique. All the inodes are unique. So if the inode represents the metadata and has the pointers to where the data is actually stored, then a hard link is the text entry that says what the file name for that file should be. So the hard links connect the text file name to an inode on the disk. So it takes both of these things in order for a file to be represented to the user as a file. A directory then is actually a text file that organizes hard links together in a hierarchy. So we can create and remove directories with makedir and removedir. We've seen those commands before. And however, because everything is a file in Unix, the directories are files too. And you can actually open up a directory in C, for example, and use commands like opendir and closedir. We can use readdir, and there's even a command called rewinddir, which resets where you're reading in the directory back upwards. And of course, the rewind name comes from when these things used to be stored on reel-to-reel spools, where they'd actually be spooled across this magnetic tape. So we still see these old terms in the Unix language, in the C programming language, and in various other commands within Unix. So the hard link that represents the directory is the single dot, and a directory hard link that represents the parent directory is the double dot. So we can actually open up those directories. I don't know if you've tried this, but you should give it a shot. So here's what happens if I open up, say, the current directory. What I get is a list of all of the text names of the files in that directory. Everything's a file. Everything is represented as a file, including what the directories are. So we can read these directories like a file from C also, as we mentioned. Here is a program that searches for the most recently modified or created directory that has a certain prefix. And in this case, I've set this target directory prefix to be brewsteb.rooms. Anything that matches that gets picked up in this loop down below, and we're looking for the directory which has been most recently modified. This particular script comes in handy for program 2, and you'll also find this in our online articles. But I just wanted to show it here that, yeah, directories can be opened up and read in C also. And as a precursor to some of the C language notes that we'll have in the next block, there's a bit of a dangerous single equals here. This is not really standard that you'd see, but it is how this particular code is constructed. So typically, of course, single equals are used for assignment, and a double equals would be used for equality. And you'd be forgiven for being mistaken that we were testing equality here between these two things, and we're actually not. In fact, the equality test is done, or the inequality test is done over here when we're comparing to null. So watch out for these single equals. They can be a bit confusing. Again, we'll talk more about that stuff when we get to the C stuff. So links. We can create a file using touch, and we'll talk more about touch in a bit. We can create this file. An inode gets allocated for us by the operating system, and a hard link is automatically created. But here's the weird part. This is why there's this split, this dichotomy between hard links and inodes. The effect of this is that a file can appear in multiple directories at the same time. The same file could even appear under different names. Even in the same directory. And I'm not entirely sure of the use cases for this, because it really flies in the face of how we typically think of files. But you could imagine a file being in one place, referred to by some name, and maybe stored in another directory where you want to update it frequently, but it's got some other name related to that function. You could imagine doing things like that. In Windows you can't, but in Unix you can. The command to manipulate these links is ln, or the link command. To remove files in C, we approximate removing, or rather, removing is the same thing as unlinking everything. So if we disconnect these hard links off of a file, then when the reference count, that is the number of hard links that are pointing at that inode, when that drops to 0, the inode gets garbage collected and the file is finally deleted. So one way to remove a file is to start unlinking file names, these hard links, off of the inode. You can't unlink a directory, but you can do it to files. So another way to remove a file would be to use the remove function in C, of course, and unlike the unlike function, remove will delete some empty directories. So if it's a file, then remove is identical to unlink, and if it's a directory, then remove is identical to remove dir. So lots of different ways to delete things in Unix. Okay, so the symbolic links, this is something a little more what we're used to. So a symbolic link is like a Windows shortcut. It's not a file. It just points to a hard link. So if you then later move around where the hard link is, the symbolic link won't be pointing to it anymore, and it breaks your symbolic link. So we can have a structure that looks like this. Down at the bottom, I'll have some inode, which points to our actual file data and their permissions and that kind of stuff. And then maybe we've got a couple of different hard links, a couple of different names pointing to that inode. And to one of them, we could have a symbolic link that's pointing to it with its own name as well. So we can refer to these files from multiple places, from multiple directions, from multiple file systems because of these links. So the symbolic links are additionally interesting because we can link across the network. So hard links only work on the local file system, but symlinks do work across the network. Alright, let's take a look at an example. So pretend I'm on a new server, but I want access back to my home directories files that are stored on the original server. So since I can't access them without logging in with, say, an SSH section, let's see if there's a way that I can link my way over there. So what I can do is, from the new server, I can use the -s switch in the link program, and I can create that to the home directory of my files, and I can give it a new name. So let me call my link out to this directory to be my files link. And then my next line, I can cd my way over through that link, and now I'm in my file system on the new server. So I've created this link on that new server that allows me access to those files. So symbolic links are pretty handy, especially, of course, when you have login accounts on all these servers and you can actually authenticate against them. Alright, so a linking example. Let's do another linking example using hard links. So in the beginning here, I'm going to make two directories, and I'm going to give them just number names. So here's directory 1 and then directory 2. So then I'm going to use this touch command, and in my current directory, in directory 1, I am going to create a file called hardlink1. And then I'm going to use the ln command without a switch, which means I'm creating a hard link. And I'm going to hard link this hardlink1 file to a new hard link stored in directory 2. And I'm going to call this one hardlink2. And then I'm going to create a symbolic link from hardlink1 in my current directory called symlink. So the structure is I have two directories, 1 and 2, each which hold a hard link called hardlink1 and hardlink2 that are hard linked together, i.e. they point to the same file. So I can use the find command, and we'll talk about find later, but find can be used to locate files on your system. And in this case, I can specify find files that are all the same file as this one here. And when it runs, it'll eventually return that both the files in directory 1, hardlink1, and in directory 2, hardlink2 are the same file. So it locates files that point to the same inode, or it locates hard links that point to the same inode. If I do an ls minus PLA capital R, which the capital R giving me a recursive look at what's happening from my current directory, I can see all of these links in place, all of these files in place. So in the current directory, I have my symbolic link that we created, and that is pointing to the hard link 1 file in directory 1. In directories 1 and 2, we can see hard links 1 and 2. And one thing to note is that the reference count over here, which is this first number after the permissions bits, this first number represents the number of, is the reference count, which is the number of hard links pointing at it. So we can see that for both of these, it's 2, meaning there are multiple names for a given file. So what's in a directory? Looking at what that ls minus PLA is returning, let's give a little deeper dive into these different columns. We mentioned that the permissions bits are on the left. This refers to reading and writing and executing, and we'll talk about those coming up here in a bit. The hard link count is the next one. Note that the parent directory hard link count is 8, meaning that there must be several different directories. How many? 8 directories in the directory above, because there's multiple places that point to it. I suppose now that I think about it, some of those could be the current directory. Whatever else is pointing at it is going to increment that number. The owner of the file is the next one. The group owner of the file or directory is the next column. Then we have size in bytes, the last modified timestamp, and then the name of the file. So we can have other things in a directory. So in addition to the hard links and symbolic links, we could have named pipes, which we'll talk about in block 4, device character special files and device block special files, which relate to hardware devices that are attached to the computer. We can have named sockets, which are part of a networking infrastructure. Lots of different things can appear in here, but they all are represented as files. All right, let's get into permissions now. So we've talked about these enough. We've looked at the chmod command a couple of times, so time to dive into this. A file in Unix has access permissions for 3 classes of users, and we call those the user class, the group class, and all others. So the user is the owner of that file, which can set all permissions. Don't confuse the term owner here with others. So that's why we use user, group, and others instead of owner. We don't want to get those confused. 3 kinds of access permissions for each one of these classes: read, write, and execute, RWX. And every single file belongs to exactly one user and at the same time to exactly one group. So let's look at what these permissions actually mean. For read permissions, that means that the file's contents can be read if the thing is a file. If it's a directory, that means that the directory's contents can be read, which means that a listing of the files in the directory can be returned. So if the read bit is set for a file or directory, these are the effects. If the write bit is set and it's a file, then that means that the file can be written to. We can change the contents of the file. If it's a directory, it means that we can add or remove or rename things inside that directory. The execute permission bit is probably the most complex here. For a file, that means that it can be executed. So if it's a program or a shell script, you can actually run it. So that has to be set first. This is what we've seen before when we say chmod plus x and then the file name. That's us setting the execute permissions. And we'll do some examples here in a bit. For a directory, if the execute permission is set, that means that you can cd into it. The file contents can be listed, i.e. you can get the contents of a file and you can even get meta information about that file if you know its name. But execute permissions don't allow you to list the names. That is part of the read permissions for the directory. So we'd need multiple permissions, multiple types of permissions to really have useful access to the information about a directory. So what's interesting is that I can list the file contents of a directory I can list the contents of a file, meaning I can read it, if I know its name. That means that you can perhaps cd into a directory if the execute permissions are set, and maybe open up a file whose name you already know. So like a .bashrc, every user has one of those. You can open that up and take a look at what they have in there. So how would you prevent that? By setting the execute permissions on the directory such that you couldn't get into there. Okay, and while I was researching the execute permissions and looking for a picture, this one came up. I'm not really sure why. It looks like what typical college students might be doing in a dorm. And I thought it was funny because the caption on it was guillotine proof, which I guess is true. Pac-Man is immune to the guillotine, I guess. Anyway, so chmod, change mod. You can change the permissions on a file by using the change mode command. So here is a sample listing. I did this with ls-pla. So here's a couple of entries. We have a HTML file and we have a directory. On the left side, we can tell the file type. So a dash if it's a file and a D if it's a directory. And there's a few others like P for, let's see, what is P for? Oh, for a pipe. Yep, P for a pipe. There's other ones out there. The user bits are here, the group, and then others in that order, UGO. And each of the three types of each of the three file permissions are represented for each of those three user classes also. So read, write, execute for the user, read, write, execute for the group, read, write, execute for all others. And if it's set, it has the letter listed. If not, it's a dash. So the way that we traditionally assign these is by using octal. So if you want to set these things, the traditional way, the original way, is that you don't use R, W, and X at all. You use the numbers associated with these things. X is assigned the value of 1, W is assigned the value of 2, and R gets 4. So for my user permission bits here, and if I've got read, write, and execute all set, I would say that that is 4 plus 2 plus 1, which is equal to 7. So I can represent the user bits with the number 7 and know that I mean RWX. For the group and all others, here I have only read and execute set. So execute's 1, read is 4, 4 plus 1 is 5. So my permissions for that particular program2 file might be 755. All right, so looking at some typical permission sets here. For a publicly viewable web page, you might set it to 644. And 644 means that as the owner, I can read and write that file. I don't need to execute it because it's an HTML file. But for all the group and others, the only thing I want them to do is to be able to read it. So I don't need them executing on the directory. I don't need them writing on the directory, or I don't need them executing or writing to this file, but I want them to be able to read it. So 644 is appropriate. For a directory, we want to add the execute bits in. That lets us cd into that directory. So by adding 1 to everything, we get 755. All right, there is an easier way to do this. So let's imagine that I start with this file above. So here's program2.html, and all the permissions have been blanked on this thing. So as we've seen before, we can use change mod and set X directly. So in this case, I'm going to say change mod and to the user permissions, I'm going to add RWX. And I'm doing that for program2.html. So when I run this command, I can see that RWX are all set for that file. I can even use comma and string together a couple different classes at once. So here I'm setting for groups, read and execute permissions, and for owner for all others, I'm setting read, write, and execute. And it turns out that that's weird. In this case, I've set all others to have more permissions than say, a security group that I'm in, which is silly. Here is what the corresponding permissions look like. So I'm going to remove the write permissions off of all others by using the minus. So it's all others, O, minus write, leaves me with this down here. So here we've got 7, and then RX and RX. R is 4, X is 1. So we've got 755 as applied to this particular file. Now, like we talked about before, setting execute permissions on a file isn't really all that useful. We don't need to execute an HTML file, but it's representative here of what the tool can do. 755. Yep, just checking things. All right, so umask. The creation mask is what defines the default permissions for new files that you create. The way that you set this thing is with the umask utility. If you don't specify an argument to umask, then it displays what your current setting is. So let's take a look at some examples. So it's a mask, which means that everything is going to be inverted. So to set the default permissions, here's our example. This is going to set default permissions on new files to give the owner full privileges. So it's inverted, which means 0, while the group and all others do not have write permissions. So here I indicate the write permission, 2. So 0 to 2 might be the default permissions that I want. So the execute permissions still often don't get set by default on new files as maybe a security hazard. So even though you set 0 here, often you'll find that what actually happens when you create a new file is that it does not have execute permissions set. So let's run through a whole example of different umask settings. So at the beginning here, if I run umask, this is what it might return, 0007. All right, so we've talked about we've talked about read, write, and execute bits. So, and we've talked about for the owner, we've talked about read, write, and execute for user, group, and all others. But there's another set of bits on the far left. This one controls the SUID, SGID, and the sticky bits. This would be setting the user ID and the group ID bits such that they stay attached to the file regardless of where the file is. Basically, it lets you take a file and run it with the effective permissions of the original creator of that file. It's pretty strange stuff, and we'll talk about it once we get to some of the security stuff at the end of the course. You can always leave them off. So for now, forget about that last bit, and it's got a 0 over there. My next command is I'm going to create a temp file. So I'll use touch to create a file, touch temp file. Then I want to ls specifically that file and get its permissions. And you can see here is what happened. Here were the permissions that were created for this thing. We can see that read and write have been set for the user, and note that the execute permission was not set. So even though I had 0 for the user, the execute permission was not set. So again, that's just something that Unix is getting in your way and taking out from you because you probably didn't intend for this to be an executable. So consider this a security feature. For the group, we have the same permission set for the group. That's where that 0 comes from. And then for all others, we have 3 blank bits, and that's because we've put 7 there. Okay, so this might work, but maybe you don't want all of the security group to have the same permissions as you as the owner by default. So let's use a different setting. So I'm going to remove the temp file that we just created. So you have to say yes to that since remove is aliased to rm-i, which means always ask. And then I'm going to change my umask setting. I'll say umask 022. So that 2 now for the group is going to remove the execute. It's going to remove the write permission for the group. So note that I don't have to specify the last 0 over here. I don't need all those leading zeros, just 1 is sufficient. Now when I say umask, it tells me what my new setting is, 0022. So now when I create a file, temp file, and look at its permissions, I can see that I as the owner have as many permissions as I'm going to get as default. And the read permissions have been set for the group and for all others. And now that we've done that, we realize, oh, I've set a umask in place that is going to make my default setting be that all users can now read my files. So that's probably not what we want either. So maybe something more like 027 would be a little safer, which would prevent the all others from accessing your files after the fact. All right, so we keep talking about groups. So what's a group? In Unix, there's the concept of a user, which is fairly easy to understand. There are user accounts, and you may have control or access to multiple user accounts, but we usually assign one user account per person. Groups, there could be lots of groups of which you are a member. When you're a member of a group, you can then have files that are owned by that group, such that you as a group can work with them wherever they are. So if you use the ID command tells us a bunch of interesting information. So when I say ID, it tells me what my user ID is on the system. And it'll also tell me my GID. This is my ID that I get known by when I'm in groups. So I don't know why it doesn't just use my original user ID, but it doesn't. You get a new ID that you are referred to in groups. Then I have a personal group that has been created for me. In the groups listing, it will tell me this is the personal group that consists of just me. So why is that? That's so that if I have a funny umask setting that is giving security permissions for group owners at the same time as whenever I'm creating files, by making all of those files also by default be attached to a security group that consists of only me, I'm not inadvertently opening up all of these files to whatever random groups are out there. So other groups that I'm a part of at one time or another, I've kind of just concatenated this onto the list, might be things associated with the eCampus, or maybe transfer learning, which was part of my AI when I was working on my master's. So these are going to be the same groups that are referred to when you use the commod command. All right, a couple other utility commands here. The du command is how you would return the total usage in kilobytes of the specified directory. So if I want to say, give me the disk usage of the current directory, it'll tell me for all the directories that are in there how many kilobytes are being used in those directories. So inode test-1 consisted of 4 kilobytes. So kind of interesting to see what's there, and I can see that what's in the current directory consists of 96 kilobytes. df is going to tell me the total usage in kilobytes for the entire file system. So if I print out my working directory, I can tell where I am, which is on this stack disk. And if I see df dot for my file system, it will tell me for all of the data that's available on that file system what the current usage is it of. We can tell how much is available, how much has been used, and what the percentage is. We can tell the mount point of it, which says where the actual data is from originally and how it has been given to us to refer to on the system that I'm currently using. So when I say pwd, I see it as NFS stack faculty, which is, and I see that because that is the name it was given when it was originally mounted to this system. All right, stat. Stat gets metadata about a file. So if I have some test file and I say stat test file, I get a ton of different information about it. I see its name, its size, the number of blocks that it occupies, which is the number of hard drive blocks that it occupies. So files don't occupy just simply bytes on the drive. They are allocated into separate blocks because blocks are faster and easier for a hard drive to read and write from than individual bytes. So the boundaries of a file might only be over a certain number of bytes, but it may occupy a number of blocks that are equal to the size of that, plus whatever, maybe there's a half of a block that's filled up by the last few bytes of a file, and then the rest of that block is wasted. But you still had to use it because you have to use a whole integer number of blocks. We can tell things about inode numbers, and then the key part here for the stat is going to be the access, modify, and change date stamps. Or the timestamps. The access timestamp tells us when a file was last read. Modify is for when the file contents were last modified, and change is updated for whenever the metadata gets changed. So if you rename it, if you change its permissions, then that one gets changed. Birth is about the creation date of that file. Strangely enough, it's unsupported on Linux. We don't get to see it there, but it does work in BSD, and of course Windows. We can see that as part of that, and that's part of the NTFS file system for Windows. If I create this test file, so if I just touch it, then that is going to update my timestamps. So I can see that my access and modify date stamps have both been modified to the current time, but also change gets modified to the same time as well because the meta information about this file was changed, which means change will update as well. So touch, a handy way to update all the timestamps on a file. Useful, again, say if you're copying a set of files from one place to the other, but you only want to change the ones that have recently changed, you can set your copy routine to look at the timestamps of all the files before it makes the copy. Let's look at touch in a little more detail here. As we talked about, it creates files and modifies timestamps, so let's look at a little deeper dive on this, including a bit of a security hazard. If I use ls-l, I can see that there's no files in the current directory. I can then touch test file to create it. Then when I do an ls-l, again, I see there is my test file in place. I can then say echo test file, and I'm going to dump text into that file to give it some size. So here you can see that the size goes from 0 to 9. So why does it have 9 bytes when the phrase that I put in there was only 8 characters long? And the reason is because the new line character was added automatically. That's what echo does. We mentioned that before. Echo always adds a new line. So the new line 9th character gets added. So it's not 10 because it's not like there's a \n that gets added. The new line character is its own character. All right, so yeah, ls-l shows us that this file now has 9 bytes in there. Now what I'm going to do is I'm going to create a new file. So I'm going to use touch with the D option and a date stamp here. So this is January 1st of 2012. And I'm going to call this one fake file. When I do an ls-l now, I can see my original file. Here's my test file. And I now see this new file I've created, which has a January 1st, 2012 date stamp. So that's pretty interesting. To make it even more interesting, I can use the -R switch on touch, which will allow me to replace the timestamps of test file with the timestamps in fake file. So when I run this command, I now have updated my test file, which has real data in it, with a fake timestamp. It was that easy to change. I didn't need root permissions to do it. Okay. This sounds terrifying, like I can just go in and update timestamps everywhere without needing to be root for those files that I own. Imagine what a headache that could be for a forensics investigation. But it turns out that the change value remains unchanged. So the meta information is being updated to the current timestamp each time you do one of these operations. So how do we get around that? The way you would do it is you would set the system time. So if you can get root access and change the system time, then you can use these touch commands to update timestamps, and the change value will be reset to the current system time. Then you could change the time back. So that could do all kinds of weird things like mess up log file entries in different parts of the system, but certainly something you could do if you really, really needed to change the timestamp on a file for all 3 of the categories. All right, and as our last slide here, we are going to be looking at some of these standard directories. We've talked about them before. The root directory is the / that refers to the whole beginning of all the files. Your home directory is a shortcut is given with tilde. You can cd to that directly. And I wanted to note here the command rm-rf, and then with a target being /*. So rm is the delete command, and R means do it recursively, so from where you are and then down into all the directories as you go. F means do it forcefully, so don't ask for anything about it. / means start at the root directory, and asterisk means do all of the files in that directory. So the command here says, in one simple character, in one simple line here, this says delete all the files on the computer. Go. So what's terrifying about this is that you might accidentally do it. So I have done this before on accident. I was trying to type this command. What this command does is it deletes all of the files in your current directory and all the directories underneath. So if you've been building a bunch of test cases and a bunch of test files, like I've done for these lectures, and then want to delete them at all, this is the command you'd use. You'd put the little dot there to say start here in the current directory and delete everything. Except I left off the dot. And this command started going through and deleting all of the files for all of the users at my university. And I just watched it go through and attempt to delete everything. And just pages and pages of text go by. And so I quickly hit Control-C as fast as I could to try to stop this operation, and then just sat there and tried to get my heart rate under control as I thought about what I'd done. But then I looked back at the scroll back and realized that all of what it was displaying was permission denied, permission denied, permission denied, permission denied, because I certainly don't have permission to delete files, and it started at the root of the system, where I certainly have no permissions, and tried to delete things from there. So didn't do any damage. I was able to halt the operation long before it got to where my user files were, but still a scary thing to do. All right. So, I hope you've learned some things about the way files are stored in Unix and you feel a little more comfortable manipulating them. If you have any questions, we'll see you on the discussion boards. Thanks!